I'm Dr. Billy Wu, and in this video we'll be looking at battery safety and exploring what happens when things go wrong. Firstly, let's look at what happens when a battery is overcharged. Initially, you can see some white smoke being given off by the battery, which comes from the decomposition of the liquid electrolyte. This is highly toxic and shouldn't be breathed in. After a while, there's a small explosion and then a small fire emerges from the battery. However, this rapidly becomes a much larger and aggressive fire with further toxic gas being given off. At one point, the fire appears to be going down. However, this becomes more aggressive again with further explosions, highlighting the dynamic nature of battery fires. So now that we've seen what can happen when batteries fail, let's have a look at different types of battery abuse. In the first instance, we can have mechanical abuse, such as something penetrating or crushing the battery. This leads to deformation of the cell, the separator being torn, and internal short circuits. Beyond this, we can have electrical abuse, whereby the battery is either overcharged or over-discharged. When this occurs, we can have small metallic dendrites, which again can cause internal short circuits within the battery. Finally, we can get thermal abuse, where extreme heat can lead to the separator collapsing, again leading to short circuits forming. This ultimately leads to what is known as thermal runaway, whereby the materials in the battery decompose exothermically, releasing toxic smoke, starting fires, and explosions. To further compound this problem, as the battery ages, generally its sensitivity to electrical and thermal abuse increases, meaning that extra care needs to be given to aged batteries. However, whilst the worst case scenario is bad, there are also many solutions being proposed, such as fire suppressing additives, which mean that even with a short circuit, thermal runaway doesn't always occur or the risk is minimized. But now that we've got an overview of the various types of abuse, let's look specifically at each one, starting with mechanical abuse. To understand mechanical abuse, let's revisit how a lithium-ion battery works. If you were to cut a cylindrical cell in half, you would find a structure similar to a toilet roll. If we take a closer look, we find the unit cell of a battery, which is made up of a copper current collector, a porous anode, usually made up of graphite, a microporous polymer separator, a porous transition metal oxide cathode, and an aluminium current collector, with all of the porous volume filled with a liquid electrolyte. When the battery is discharged, lithium ions are liberated from the anode with the release of an electron. This lithium ion swims through the electrolyte towards the cathode. The electron, on the other hand, can't flow through the electrolyte and instead goes through an external circuit where useful electrical work is extracted. Both of these are then recombined at the cathode. When the battery is recharged, the opposite process occurs whereby the lithium ions go back towards the anode. Now, if a battery is mechanically abused, such as if a nail were to penetrate it, this would be detrimental. The nail now allows for electrons to flow from the anode to the cathode, but in an uncontrolled way with a large amount of current. The resulting short circuit therefore generates a significant amount of heat, which has the potential to lead to thermal runaway. Of course, what I showed there was a simplified cartoon, so let's have a look at a real-world system. Here you can see a high-speed X-ray radiograph scan of a battery during a nail penetration test. This is similar to an X-ray of a hand, allowing us to see inside the battery without taking it apart. Initially, you see the nail penetrating the external protective casing of the battery. Then, as the nail gets deeper, this short circuits the cell, allowing for current to flow through the layers of the battery. This large flow of current then leads to a significant heat generation, melting the components and the ultimate failure of the battery. Next, let's have a closer look at what happens during electrical abuse, which we can break down into two main types, overcharge and over-discharge. Firstly, let's look at overcharge. We saw before that lithium goes from the cathode to the anode during charge with the limits defined by our definitions of 0 to 100% state of charge. Now, in reality, there's excess lithium in a battery that allows for a small amount of overcharging, though this normally results in reduced lifetime. Eventually, the graphite anode is no longer able to hold all the lithium, and some is instead plated on the anode, which can form dendrites that can short circuit the battery. Furthermore, as the voltage of the cathode gets higher, this leads to the decomposition of the liquid electrolyte, forming gases which cause the cell to bulge, and also the cathode becomes increasingly unstable, leading to transition metal dissolution. Then, as we continue to overcharge the battery, this can lead to the decomposition of the protective solid electrolyte interface layer, as well as the decomposition of the anode. These processes combined can lead to significant exothermic processes, which ultimately lead to the battery rupture. Therefore, overcharge can lead to lithium plating or internal shorts, electrolyte decomposition, transition metal dissolution at the cathode, SEI layer decomposition, and ultimately battery thermal runaway. Now, let's have a look at what happens during over-discharge of a battery. Again, we define the normal operation of a battery as being between 0 and 100% state of charge. However, the battery again has some extra lithium, which means that it can actually be slightly over-discharged, usually at the cost of battery lifetime. Then, as we keep over-discharging the battery, the protective SEI layer can again decompose, allowing for the electrolyte to come in contact with fresh anode material, which leads to accelerated degradation. As we continue, we run out of lithium, and then the copper, which acts as the current collector, starts to dissolve into the electrolyte. As we continue this, it can eventually form copper dendrites, which can internally short-circuit the battery in a similar way to lithium dendrites. Therefore, over-discharge can lead to the decomposition of the SEI layer and formation of copper dendrites, as well as generate gases such as carbon monoxide, carbon dioxide, hydrogen, and oxygen. Now, in most cases, a battery can be recharged after over-discharge. However, the reformed SEI in general is less stable, and there's increased risk of failure due to potential copper dendrites. And finally, let's have a closer look at perhaps the most important element of battery abuse, which is the thermal considerations, whereby extreme heat can cause effects such as the separator collapse and thermal decomposition of the battery materials. Now, in order to understand thermal abuse, let's revisit the structure of a battery, where the solid electrolyte interface, or SEI, is one of the key considerations. In most battery systems, the liquid electrolyte is thermodynamically unstable with lithiated graphite. This basically means that this system shouldn't have good lifetime. However, the protective SEI layer stabilizes the graphite, allowing the battery to work. As the battery is heated to about 70 degrees, this SEI layer can decompose, revealing fresh graphite surfaces to the reactive electrolyte. As heating continues, the electrolyte and anode react with each other in an exothermic process which generates further heat. At approximately 130 degrees, the polymer separator melts, allowing the anode and cathode to touch each other, creating an internal short circuit which leads to large amounts of current and further heating. At approximately 200 degrees, the electrolyte then decomposes, leading to the release of various gases, some of which include hydrofluoric acid, which is one of the more nasty compounds. Finally, at about 300 degrees, the transition metal oxide cathode decomposes, releasing oxygen, leading to thermal runaway. Now, this last point is important, as fires generally need three things to sustain itself: fuel, heat, and oxygen. And in the case of battery fires, they can generate their own oxygen, which means that firefighting solutions need to take this into account. So, if we were then to view all of these processes, we can see that we start with the decomposition of the SEI, which leads to the exothermic reaction of the anode with the electrolyte, the subsequent melting of the polymer separator, short circuits, and decomposition of the electrodes and the electrolyte, leading to thermal runaway. However, not all batteries are equal in terms of safety, as we can see from the right-hand side plot, which is adapted from the excellent review paper from Shuning Feng at Tsinghua University. On the vertical axis, we have delta H, which represents the enthalpy, and Q, which represents the maximum heat generation rate. And then, on the horizontal axis, we have the temperature of the reaction. Now, for the various battery components, each will have a different enthalpy change, which you can think of as the total energy in joules per gram of that reaction. Depending on the reactivity, each reaction will also have a maximum heat generation rate in watts per gram, which you can think of as how fast the heat is being released. So a reaction with a high enthalpy change and high heat release rate will have a very big and very aggressive thermal process. Also of interest are the temperatures at which they start, end, and also the temperature at which the peak reaction rate is achieved. One of the first reactions of interest is the SEI layer decomposition and its regeneration, both of which are exothermic, with the regeneration at high temperatures containing significantly more energy. Once the battery reaches 130 degrees, the polymer separator, which is normally made of polypropylene or polyethylene, melts, which is actually endothermic. However, this can cause an internal short circuit, which can be quite exothermic. Clearly, the melting of the separator is an important step in thermal runaway, and there are some solutions such as ceramic-coated separators which can delay the onset of separator melting to over 200 degrees, but this generally adds cost and weight. Now, if we start looking at electrode materials, lithium cobalt oxide, which was used in first-generation lithium-ion batteries, generally has one of the lowest onset temperatures for decomposition, which has led in part to its gradual phase-out. In modern electric vehicles, NMC or nickel manganese cobalt oxides and NCA or nickel cobalt aluminium oxides are now normally used, with both materials generally having a higher onset temperature, with low nickel NMC materials generally being less dangerous in terms of total energy, though it should be noted that there is a movement towards high nickel compositions which have a higher capacity but at the cost of safety. Then we have LFP or lithium iron phosphate, which has in recent years seen renewed interest due to the low-cost nature of iron, but also because of its safety characteristics. Here you can see LFP has both a high onset temperature, but also a low heat release rate and total heat energy, which makes it much safer. Finally, we have the highly exothermic process associated with the graphite and electrolyte decomposition, which ultimately leads to the combustion of the entire battery, which is the worst case scenario. So, to summarize, lithium-ion batteries can pose significant risk if not properly managed, with consequences such as toxic smoke, fire, and explosion. Types of abuse which can cause this include mechanical piercing or deformation, which can tear the separator leading to short circuits. Electrical abuse in the form of overcharge and over-discharge, where we can form lithium dendrites on overcharge as well as electrolyte decomposition, and on over-discharge we can dissolve the copper current collector, forming copper dendrites. And finally we have thermal abuse, which results in melting of the separator, decomposition of various battery components, and thermal runaway. The challenge in managing these factors are then compounded when the battery is aged. Though some batteries are safer than others, such as lithium iron phosphate with a ceramic coated separator. But the key takeaway is that careful management of lithium ion batteries is needed in order to make sure that these thermal runaway events don't occur. So this concludes the video on battery safety, which explores what happens when batteries go wrong, and I hope that you found the content useful.